Okay, so now we get to the good stuff. Now we want to figure out just how the uncertainty in our distance and in our speed have affected the prediction that we made of our time. So we know that our time that we're calculating is a variable that is dependent upon both the distance and the velocity. And the time that we're going to estimate is in hours. It's always important to keep track of units because they, as you learned in your lab, could help you. So then we have to go through each of our independent variables. In this case, this is the dependent, and each of these are our independent variables. So we're going to write each of these independent variables here. I'm not going to be using these things because I only have two independent variables. The independent variable d is our distance. We said that that had a mean value of 57. And I'm just calling it a mean. I mean the most general value. 57, it's plus or minus 1. We don't have any confidence for that. And the units are miles. Our velocity, we said, was 70 miles per hour, plus or minus 3.64 at 95% confidence. We should also go through and say where we got the source of that uncertainty. In the case of our distance, it was an instrumental uncertainty. In the case of velocity, it was both instrumental and statistical. So now we want to know what time we predicted. So this is the mean value of the time. It was 0.814 hours, or the 48.85 minutes. Now the question is, how different could this variable, this dependent variable, how much dependence does it really have on the independent variables d and v? That's what this box is supposed to help you figure out, this box plus this equation. So what we want to do first is write t with a little subscript d and t with a little subscript v. So we're just asking ourselves, let's calculate t, now imagining that that time is off because our distance is off by its maximum amount. So we're going to redo this equation here. But now instead of just the regular value for d, we're going to plug in d plus its maximum offset. So we're going to do 57 plus 1, and that's miles, divided by our 70 miles per hour. And again, our offset is still always going to be calculating number of hours. That's going to give us a value of, I'm having to write over here because I'm writing big, 0.828. Yeah, it helps to write small with this. And then that we ask ourselves, how different, so that's what this delta is here, how different is that time going to be from our original time here? So then we're going to difference 0.814 with the 0.828. So we're going to get a value of negative 0.01429. And we're going to do the same thing with velocity. The question is, if the velocity is off by some amount, how much does that affect our time? So we're going to be using this formula again, this formula up here. But instead of just using the regular old mean velocity, we're going to use the mean velocity plus its maximum offset. So now we're going to do 57 miles divided by 70 plus 3.64 miles per hour. And that's going to give us now a time of 0.774 hours, and we're going to difference that time. Once again, this delta means difference. That's with respect to velocity. We're going to difference these two so that we have 0.814 minus 0.774. This is the most fun you've ever had on a car trip. Difference those two values and we get 0.04. What does any of this mean? What do these numbers mean? Well, these numbers have meaning when we compare them and when we plug them into this equation. So we want to know how off our time could be. We didn't measure time, we calculated it. Since we didn't actually measure it, we can't do any of that statistical uncertainty nonsense, we don't have any instrumental uncertainty nonsense, we've just got the pieces that made up the time. We've got distance and we've got velocity. So we want to know if we calculated the time and we screwed up the distance, if we calculated the time, we screwed up the velocity, how those uncertainties, these numbers that seem like nonsense, those things are going to contribute, they're going to add into here to tell us just how different our time could be. So this uncertainty in the time is going to be found then by taking this negative 0.014, and once again that's still in hours, squaring it and then adding to it the 0.04 hours and squaring that. And that gives us an uncertainty of 0.04271 hours. So what we're saying is that this time that we predicted, of 0.814 hours, has some uncertainty on it because the things we used to calculate it had some uncertainty. We've had to propagate through the uncertainty on the things that we measured to figure out the uncertainty on the thing that we predicted. So this uncertainty that we just predicted was 0.0427, and that's at 95% confidence. Since this hour thing's sort of nonsense, no one really thinks in fractions of hours, we can write this out at 48.85 plus or minus, and then we can just change this nonsense of hours into minutes and get 2.562 minutes. What this means is that we may not have arrived at exactly 48.85 minutes because that time that we predicted had within it some uncertainty because of the things that we used to predict it having some uncertainty. So it may not have taken exactly 48.85 minutes. It could take anywhere from 46 to 51.4 minutes, and we'll still be right. This whole range of possibilities, this roughly 5-minute range, is still okay. And if you're curious as to why this uncertainty exists, what's causing this uncertainty, you can go look at these numbers up here. You can compare each of the numbers that you see. So this difference of offset with the mean, we've got 0.04 and we've got negative 0.014. Now the negative doesn't really matter because again these terms get squared, so the negative goes away. So we can just compare the absolute values and we'll see that we're comparing a 0.04 with a 0.014. This one is almost 4 times as large as this one. And that means that our velocity, the uncertainty or the variance in the velocity, actually is much greater than the uncertainty in our distance. So whose fault is it that you didn't get this exact mean value right on the dot? Well, it's your friend's fault. Your friend is driving with enough variance that causes enough uncertainty in the velocity that when propagated through causes an uncertainty in the time that still allows you to be right. But does mean that your friend should probably be using cruise control. You figured out that your friend was the cause of all your ills, and at this point no one cares anymore, but you still care. So you're going to use your prediction worksheet. So the quantity given to you, not by your TA, but the friend, was the distance, and that distance was 57 miles. And you were asked to predict the time. The question is, how do you do that? You know that time is going to be distance divided by velocity. You know the velocity is going to be 70 plus 3.64 miles per hour, plus or minus. And you know that distance is going to be 57. And you know too that this thing might have some uncertainty of plus or minus 1 mile. So 57 plus or minus 1. So then that allowed you to predict a time of 48.85 plus or minus 2.562 minutes. So that's actually the quantity that you'd write down here. Time equals 48.85 plus or minus 2.562 minutes at 95% confidence. So on your road trip, you only got the one shot. Your trial showed that it was 51 minutes. And is this in the interval? Yes, barely. So you look at your friend knowing that you've won this, wanting to move on with your life.